Here we are starting lesson 2 for our unit 7 on our colligative properties. The first thing we're going to talk about is solubility again. We touched on it in the last lesson, but we're going to go a little bit more in depth for this lesson. Most important thing to remember is hydrogen bonding and solubility. Hydrogen bonding is fun. Never forget that. And hydrogen bonding increases the solubility in water. You can see here that with formaldehyde, that molecule there, will hydrogen bond with this hydrogen to create very great solubility of formaldehyde in water. Now looking at ionic compounds, such as sodium chloride, when the ionic compounds dissolve in water, the compounds break down into cations, positive ions, and anions, negative ions. Water molecules surround those ions. And remember those partial charges on water? The negatively charged parts of those ions will attract the positive part of water, the hydrogen, and the positively charged ions will attract the negative parts of water. Now, non-ionic compounds are a little bit different. So these polar non-ionic compounds will dissolve in water if they're soluble in water. They do not break down into ions. But like ions, they have a partial charge. So those partial charges will interact with the polar molecule that is water. The positive part of the molecule will be attracted by the negative oxygen, and the negative part of the molecule will be attracted by the positive hydrogen. So it'll kind of look like this. So here's our ionic compound. You can see that the negative ion of the compound is attracted to the positive hydrogens, and the positive ion is attracted by the negative oxygen. And likewise, with the non-ionic compounds, you can see you have a polar molecule here interacting with the water. The positive part of the molecule interacts with the oxygen of the water, and the negative part interacts with the hydrogens of the water. So that comes to electrolytes. Electrolytic solutions. These are solutes that form ions when they're dissolved in water. For example, sodium chloride will dissociate into a positive sodium and a negative chloride when dissolved in water. You can see here we start with our big chunk of sodium chloride put into water, and it dissolves into the different ions. The blue ones are the positive sodium, and the red ones are the negative chloride. Otherwise, non-electrolyte solutions. These do not form ions when dissolved in water. For example, glucose, sugar. The molecules will separate from one another, but they will not break down into ions. So you'll have a nice clump of glucose molecules before put in water, and those glucose molecules will break apart from one another when dissolved. Just like here, you can see that the clumps of glucose are together. They're clumped together. Then when you put them in water, when they dissolve, they break apart using the polarity from the water. Because glucose is a polar molecule. It's a sugar. It has some oxygens and hydrogens and carbons. So let's talk about some other colligative properties. Colligative properties are properties of solution that depend on the concentration of the solute particles. It doesn't matter what they are, it matters how much of them are there. Kind of like, how comfortable are you in a room when there are 4 people as opposed to 500? That's a colligative property. So the 4 we are going to talk about is vapor pressure lowering, boiling point elevation, freezing point depression, and increase in osmotic pressure. We're going to learn through osmosis. We must be in a pool. Anyway, vapor pressure. We've talked about vapor pressure. Think about having tea. There's always a little bit of steam on top of your tea because it's hot, because those molecules have a lot of energy. And vapor pressure is a measurement of that pressure. and it's in equilibrium. The rate of evaporation is equal to the rate of condensation, so it's becoming gas at the same rate as the gas is becoming liquid. And a liquid will boil when the vapor pressure is equal to the atmospheric pressure, usually about 1 atmosphere. Vapor pressure increases with increasing temperature. So vapor pressure lowering. Have you ever put salt in your water when you're making mac and cheese? I know I do. Well, pretty interesting. It doesn't always work. You would think they do that to make it boil faster. However, that's not the case. When a solute with a high boiling point, salt, is dissolved in a solvent, water, the vapor pressure of that solvent will decrease. The boiling point of any solvent will increase when a high boiling point solute is added. Sorry, there's a little typo here. This should be solute. So your solute will bring up the boiling point. It will make it harder to boil. So when you're adding salts to your water that you're trying to boil, you are not trying to make it boil faster. You're trying to make it boil hotter so your noodles will cook faster. It takes a little while, but think about that the next time you're making noodles. Let's look at a nice solution of sodium chloride here. Pure water. The vapor pressure at 100 degrees Celsius, which we know is the normal boiling point of water. The vapor pressure there in millimeters of mercury is 760. It's our vapor pressure right before it boils. Boiling point at 1 atmosphere of pure water is 100 degrees Celsius. Now let's go up to a little bit stronger of a solution. This just tells you how much is in the solution. The M there, 0.5 molar. When you increase that concentration, look what happens to the vapor pressure at 100 degrees. It's a little bit lower. So it has to be a little bit hotter to boil. And now, looking all the way at the end here, the 4 molar solution, the very concentrated, look how much higher the boiling point is, 104. Adding a high boiling point solute will increase the boiling point of water, make it hotter, have to boil at a hotter temperature. The same with freezing point depression. So if anyone is like me, I'm a little clumsy when it comes to ice, and by a little I mean a lot. And this freezing point depression, the rock salt, is a godsend. It goes when a solute with a high boiling point is dissolved in a solvent, the freezing point of a solution will decrease. It'll become harder to freeze or lower the temperature of the freezing. So that comes in handy with ice. Pure water freezing point is 0 degrees. Now you make it a little bit of a solution of sodium chloride in water. It goes to about -1. It has to be -1 before things freeze. Double that, make it a little more concentrated. Has to be -2 degrees Celsius. Double it again, about -4. It's very useful for us, especially here in Ohio where it snows and ices and gets pretty icy. The freezing point depression is very helpful. So osmotic pressure. Osmotic pressure is a little hard to understand. So I'll give you a nice, easy explanation here. So osmotic pressure is the pressure that would have to be applied to stop the flow of water molecules in osmosis. So what normally happens here is here's our water, here's our solute. You see the salt dissolved in there. So what happens? Think biology. Osmosis is the movement of water, diffusion of water. So since there's a higher concentration of solute over here than there is over here, the water is going to flow towards the solute in order to even out the concentration. Now it takes a little bit of pressure to stop that. So you can see in the images here, in number 2, the water from side B has diffused over into side A. See the volume change? Osmotic pressure is this arrow. It's the pressure that keeps the solution from having osmosis over this barrier. It keeps B from coming into A. Oops.